Hopefully my Facebook also got sound. Okay, so welcome to the next class. Again, I stated before, the beauty of this class, dia tak keluar exam. The beauty of this class, dia tak keluar exam. Okay, so what is the topic today? Today we're going to cover about uh, logistic regression. Okay, so as you can see on the screen now, I'm putting up a paper by J.S. Kramer, published in November 2002. You can Google it up. Origins of Logistic Regression by J.S. Kramer. Okay, so there's been a lot of argument about who came up with the origins of logistic regression. Initially, I thought it was Baker from 1961, but now it was not. It was much earlier than that. Okay, so who was the first one to came up with this idea of logistic regression? Okay, in fact, it came from a person from Belgium. Okay, a person from Belgium. The name of the person is Alphonse Quetelet. I'm not sure if I pronounce correctly. Okay, Alphonse Quetelet. Uh, so, and he tried to basically he was trying to come up with a model for population growth, and he asked his student, Pierre Francois Verhulst, a Belgian. So Verhulst looked at the problem, and he came up with a formula, yeah, to calculate for how to predict the population growth. Okay, and using three data point from the population growth of America, he came out with this formula. As you can see, the last part, this one. Okay, so this is what he called the logistic function. So Verhulst came up with the term for this logistic function. As you can see, it looks very familiar because it looks very similar like our logistic regression formula. Okay, yeah. I got message coming in. Okay. Okay, not you all. So the whole point, the important thing is, uh, it's not any from any of the students, so they have no problem coming in. Okay, I can see Sumi is already in. Okay, so this is what the formula that Verhulst came up with, and it was published in Correspondence of Mathematics of Physics in 1838. Okay, in 1838. So basically, he used this formula to calculate the cost of population for France, Belgium, Essex, and Russia for periods up to 1833. Okay, so why, but what happened was this idea did not catch, and it sort of died off, and it was never used further. But way back in 1920, so way back in 1920, Pearl and Reed, Pearl and Reed. So Pearl is student of Carl Pearson. Pearl was a student of Carl Pearson. So Pearl and Reed was trying to study the population growth of the United States. They were not aware of Verhulst's work. Okay, they were not aware of Verhulst's work. And they arrived independently at the logistic curve concept. Okay. So, and when
Prof.
they, yes?
Oh, sorry, Prof. The screen is very blurred.
Okay, don't worry. I'm going to share the screen now. So I'm going to share screen now. Okay. Oh, sorry. I think I know why. My attendance one is still affecting the whole thing. All right. Okay. So I'm going to share this screen. This. Okay. I hope that's clear now. Okay.
Yeah,
Okay.
okay, bro. Thanks.
Okay. So let's. I'm going to check the other screen. Yeah. Okay. I'm still spotlighted. Okay. Okay. So Paul and Reed came up with the same idea on their own, and they managed to show that the census figures, the curve fits very well for the period between 1790 to 1910. After that, it no longer fits because of the war. Okay. So, so what happened was, the nice thing they realized that this logistic curve can be used for almost any living population, from fruit flies to the human population of the French colonies in North Africa. Okay, so there's a lot of these things being applied for. Okay, so who was that? There was Raymond Pearl and Lowell J. Reed. Okay, so this one is the part where they apply logistic regression for population growth. But what we are interested in is the application of multiple logistic regression inside medical research as what is being applied nowadays. Okay, who was the person responsible? Okay, it was. Okay, I'm going to scroll up. Okay, okay. So it was the person who came up with all these calculations. Can you hear me?
Can,
Boleh?
Prof.
Yes, bro.
Okay. Because on my screen came out the message internet putus. Okay. So the one that we are used to, the statistic that we are used to, okay, was introduced by this person, Gadam, 1933, and Bliss, 1934. Okay. Uh, so the person who really came up with all this calculation, whatever that we use nowadays, was really Charles Bliss. Charles Bliss is one of the figures that was very much discussed in the book uh, Lady Tasting Tea. He's a guy who lost his job in America, ended up going to Leningrad. Then he was caught during the purge of the Stalin's purge, and he managed to escape back to America. But once in America, he was labeled as a socialist, and he ended up having difficulties in getting work done. Okay, so that is Charles Bliss. But Charles Bliss is an entomologist. Okay, so Charles Bliss, okay, was the one who came out with what we are the whatever we're doing nowadays. Okay, okay. So basically, what happened was, okay, I'm going to push it forward all the way until the Bliss part. Okay, so basically, Bliss published two brief notes in Science, but instead of the word logistic, he used the term Probit. He used the term Probit, and he called it the Probit curve instead of the logistic curve. Okay, so I would like you to remember the person who came up with the term logistic curve was Verhulst way back in 1837, 1838. Okay, so when Pearl and Reed rediscovered the topic in 1920, they did not call it logistic until the paper they published in 1922, because that's when they realized that it was originally discovered by another person, and they stated about the person's contribution in their paper in 1922. Okay, when Gadam and Bliss came out with the same idea but applying the theory into what we are doing nowadays, what we call logistic regression, Charles Bliss uh, used the term Probit. Use the term Probit. Another person called Bergson wrote a lot of papers, lot of papers about this. But Bergson, I think you can use found Bergson's name again and again in statistics and epidemiology. Okay. But Bergson is someone who likes to argue, and he ended up uh, arguing with a lot of people. Okay, and he wrote papers condemning about earlier papers about earlier authors. So he was not that well accepted. Okay, so basically we have two terms here. So one we have this probit. The probit came from the term for probability unit. Okay, then we have the term logistic. Okay, so their idea is similar. The idea is the curve is similar. Everything is similar. The only difference was the term. The difference is the term. Bergson was responsible for perpetuating the argument which one is better, is it probit or is it logistic. Okay, I'm not going to touch on that. Yeah. But what we're interested in is how we apply that thing in uh, our use day to day. As mentioned now, this is the person, Joseph Bergson. Yeah. So he wrote more about it. But the person who came up with all the other terms like maximum likelihood ratio, maximum likelihood estimators, MLE, that one was Charles Bliss, not Bergson. Okay, so what Bergson did, his advocacy was on minimum chi-square estimation instead, not on maximum likelihood estimators. So he wrote a lot of papers, even all the way till 1980. Okay, so whatever it is, what is the key point here? Okay, logistic is not something that is established, unlike mental Hansel. Okay, so when did this thing become more established? Okay, because of the use of software in analysis. And inside the software, they use the term logistic regression. So that's why the term logistic regression became popular nowadays, no longer probit analysis. Okay. So where was the term probit analysis used? Probit analysis was mostly used when they're studying drugs, the effect of drugs. Okay. For us in social studies, where we're trying to find the effect. Sorry. Tak. Ini saya punya check tu untuk bayar duit rumah. Ya, ya. Ya, ya. Okay. Terima kasih kerana confirm. Tak apa. Okay, terima kasih. Salam. My apologies, guys. Basically, a house that I bought 22 years ago was finally ready. Not a house, an apartment unit. So I just made the final payment on the house, and the bank would like to confirm whether it was I who made the payment. Okay, takut, because it was quite a large amount. So that was very good of Maybank, calling to confirm the payment of the check for that large amount. Okay. Okay, so which one is better? Which one is better? Is it logistic regression better or is it probit better? Okay, even with maximum likelihood estimation. Okay, so in terms of the use of computer, logit or logistic regression is easier. Okay, is easier. And the best part, computer makes it much more faster. Okay, so the speed in which the new technique become widely used is considerably influenced by the simplicity or otherwise of the calculation that it requires. Okay, so next door to the lecture room in which the Probit method is expounded, one may still find the laboratory in which the workers compute their activities by the much less sophisticated Behren's Rig-Munch method. So what they're trying to say that we may have many different methods. We have mental Hansel, we have Probit, we have multiple regression. But the whole point here right now, the way each one of these techniques is applied is usually to different things. It's usually to different things. Probit method is, although similar to logistic, it is applied to effect of drugs, population calculation, so on and so forth. For us, when we use logistic regression, we are using it trying to find among the categorical data. So right now, people on the internet is having trouble because of that. All right. So that is the introduction about that. So in short, in summary, okay, whatever that we do nowadays, okay, is in fact through the work of all these different people, but each one is doing their work in their respective field. Okay, and when they came up with this work on Probit or logit, they tend to use the word by using slide rule, mechanical calculating machines, okay, and the use of because remember they have to convert the data into log. They have to convert the data into log, natural log. So in the end, with the advent of computers, the things become much more faster. But the first person to really use this in social studies like us, similar like us, is Cox. Okay, you can read up about her. Is a lady. Uh, she inside the book Lady Tasting Tea. Okay. Uh, so Cox was the one who came up with this method that we use nowadays. Okay, remember we have the word uh, the R square, the Cox one. Okay, so that one came from her. Okay, so this is the 1960s. All right. Okay, so right now I'm trying to say right now, because of the advent of computer, logit become more popular than Probit. Logit become more popular than Probit. So right now you look here, there's a list here. Okay. If you remember, I told you about the history of computer, SPSS. Okay. In the 1990s, we started having the SPSS version for the desktop. Yeah, for the desktop. So not surprisingly, logistic regression became more popular. So nowadays, in fact, to be frank with you all, when I was studying, we never heard of the term Probit. Okay, so in with that introduction about the history of logistic regression, okay, I hope that's clear. So I'm going to start with the usual slides. This time the slides came from Prof. Ayub or Prof. Link 9. Why I use his slide? Because I find it very easy to explain using his slide. So I'm just going to start with his slide, and as usual, the slide is available on drtamil.me. Okay. Okay, I'm going to share. I'm going to change my screen now. Okay. I'm going to stop sharing this. Okay. Any question about the history of logistic regression? So I hope you understand logistic regression For us, the way we apply it was really based on the work of Cox. It was a series of papers published. There were about 12 papers published in 1960s. You can look it up. Then that's when you will realize that her idea is similar to what we are doing nowadays. Okay, okay. Let me stop the. Okay, right now I'm having some problem. My apologies. Okay, I'm looking at three different screens, trying to figure out where the hell I am. Okay, so this is green screen. Can you capture, change to become my website. So my website is this. All right. Okay, so I'm back on my website. So I can close this screen. Okay, so I'm going to stop sharing the screen. Boom. All right. So the share screen to change. Now I am going to share back the new screen before David complain doctor cannot see. Blur. Okay. Screen 3. Okay. So you should be able to see the same screen like what I'm seeing now, which is the screen of my website. Okay. So that was the history of logistic regression. So now let's look at the logistic regression per se. Okay. So, okay. Right now my mouse is on the wrong screen. Okay. So please ignore the display here. This one, the Baker 1961, is not for our logistic regression. Baker took advantage of the work done by Cox to apply the similar idea into Rush. So that's what happened. And that's why 1960 was a paper by Cox. Baker was in 1961. He applied whatever that was yeah, I got another message. Okay, so basically Baker took the work from Cox and applied the same idea inside Rush analysis. Okay, so let's go back to the lecture at hand. So the lecture at hand is about Rush, about logistic regression. We got Rush saja. Okay, so as you can see, the notes is not mine. The notes belong to Link 9. Okay. He has a fantastic set of notes. So right now I'm going to use his notes just to start the lecture. Along the way, I'll be jumping in and out. Okay, I'll be jumping in and out so that I can cover uh, the explanation. Okay, so this one is about logistic regression by Prof. Lin 9. Okay, very good set of slides. Okay, so he does not cover history. He just explain what is the use of logistic regression. Okay, and he goes into all the different steps of handling multiple logistic regression and how to analyze and interpret the data. Okay, okay. So in this example, Prof. Ling Nine used the term trying to find the relationship cholesterol, between cholesterol and age. Okay, men are like coconut. The older they are, the more oily they become. And I'm not using wine as example. I'm using coconut. The older is the coconut, the more oily it is. So here in this case, in this scenario, the older is your age, the higher is your level of cholesterol. However, if you have the outcome as in categorical, okay, normal cholesterol and hypercholesterolemia, you cannot use a straight line. You cannot use a straight line. Okay, you cannot use a, as you can see here, because there's nothing in between. Okay, there's nothing in between. Okay, there's nothing in between. So you just have 0, no hypercholesterolemia, and then you have 1. Yeah, you have the hypercholesterolemia. So if you're trying to use linear regression, it won't work because you cannot draw a straight line. There's nothing there in the middle. There's nothing there in the middle. Okay. So sorry I cannot use the laser pointer here because this one is the PDF file. Okay. But if you are trying to look at the probability of developing hypercholesterolemia based on the person's age, the higher is your age, the higher is the risk of you developing hypercholesterolemia. Okay. So you can see there, the higher is your age, the higher is the chance of you developing hypercholesterolemia. Okay. So if you're looking in terms of risk, it looks like something like this. It looks something like this. So the probability of you developing hypercholesterolemia is higher as the older you get. Okay. Now, instead of having those in terms of probability, you convert it to become odds. Okay. Why? Because the probability is still not a straight line. It is still not a straight line. Instead, if you convert it to become odds, it becomes worse. It becomes this kind of curve. But as any of you realize, if you get this kind of curve, if you log this value, it will become a straight line like this. And this one you can do like similar like a linear regression, because now it is a straight line. So if you use the probability like this, it is not a straight line. If you have the odds p over 1 minus p, it become like this. But if you log the odds, it become a straight line. Okay, so this is the part where I jump to the, okay, just check. Okay, so this is the formula. This beta, each one of these beta, they are basically the odds ratio. If you exponent the beta, and what are these beta? These are the what we call the MLE, the maximum likelihood estimators. They become the odds ratio. Okay, so we have explanation about that. Okay, so this one, remember this one? If you do like this, you can get a straight line. You do like this, you can get a straight line. But based on this one, since you can get this a straight line, you can use the standard linear regression approach. So basically, it is what we call the generalized linear regression. So something that is not continuous, but you can generalize the idea of linear regression to this same concept, because now after you log it, it became similar like linear regression. By the way, please take note, this is not log 10. This is not log 10. This is natural log. Okay. Okay. So let us dive deep into that. Okay. Okay. So if you have okay, let's convert the risk and odds. Okay. Risk and odds are not the same. Risk and odds are not the same. Why? Risk, the denominator include the numerator. For odds, the denominator does not include the numerator. Okay. Okay. So therefore, if you say the risk here is 2 out of 10, so 2 out of 10 here is 0.2. But when you change it to become odds, it's no longer 0.2. It became 0.25 because this one is not 0.2 divided by 10. It's not 0.2 divided by 1. It is 0.2 divided by 1 minus 0.2. So 1 minus 0.2 is 0.25. Sorry. So minus 0.1 minus 0.2 is 0.8. 0.2 divided by 0.8 is 0.25. So that's why it is different. So odds is not the same like risk. That's why when you do logistic regression, you get odds. You get odds. You don't get risk. Okay? So that is a big problem for most of the traditional lecturers because they have been trained that whenever you do a study using case control, you get odds. Whenever you do a study based on cohort, you're supposed to get risk. Okay. So therefore, whenever we do logistic regression and we present the data as odds ratio, you end up being queried by the lecturers. How can you get odds ratio from a study that is not a case control study? Okay, so that is the problem. Okay, okay. So the more explanation is okay. So risk ratio is relative risk. Okay, so risk. Sorry, this is not risk ratio. This one. Okay, this one is about. This one is. I know we use the term risk ratio here, but I want you to use the term relative risk. I want you to use the term relative risk. So relative risk. Why use relative risk, not risk ratio? Because the term ratio itself says that the below part should not include the numerator, so it's very difficult. But here in this case, we have two groups. We have the group who are exposed, and we have the group who are non-exposed. Okay. So for the group who are exposed, okay, how many develop the disease? For the group who are not exposed, how many develop the disease? So that's the risk ratio. For odds ratio, is the odds of getting the disease among the exposed and the odds of getting the disease among the non-exposed. So it's different, eh? So this one, A is A divided by A plus B. This one is C divided by C plus D. This one is ADBC. This one is ADBC, but for the respective group. Okay. Okay, so odds ratio of 3 means the odds of getting a disease among the exposed is 3 times of those among the non-exposed. And the odds ratio of 3 for smoking with lung cancer, the odds of those getting lung cancer among smokers is 3 times of that among the non-smokers. So you are comparing two different groups. So that is the big difference about odds ratio. Okay, so I know a lot of people is getting confused about this, why they are not the same. Okay. I prepared an Excel spreadsheet to show the difference in these two. So I'm going to open up that slide. Okay. Okay. Let's see whether I can open this thing. It is available. It is available on that on the same website. Okay. I need to get to my desktop first. Okay. Okay, I'm going to stop sharing the screen I shared earlier. I'm going to give you a new screen. So the new screen is of my Excel spreadsheet. Okay, so let's see whether I can get the Excel spreadsheet. Okay, give me some time here. Okay, I got the Excel spreadsheet already there. Okay, I hope you can see the spreadsheet. Okay, as for me, my screen tengah havoc. Why havoc? I also don't know. Suddenly got purple color come out. Okay, so let's change this. Ah, apparently my spotlight screen come out green in color. Let's see whether it's the same thing happening to FB. Okay, FB is okay. So only my Teams is coming out wrong. Okay, the device setting. Okay, much better. Okay, my apologies. There's a problem with technology. You end up with weird results. Okay, so let me explain the table that I put up just now. Okay, I'm going to move my mouse there. Okay, I hope you can see the mouse. Okay, if you have 100 cases, you have 100 cases. Okay, and out of the 100 cases, 10 of them have high cholesterol level, 90 of them become normal. So you can see the probability here is 1 over 10, 2 over 10, 3 over 10, so on and so forth. So it is following exactly like the probability. But once you convert the probability to become odds, okay, so here you can see here this is odds, and odds is 10 over 90, 20 over 80, so on and so forth. So it is different. These are the odds. Okay, so if we natural log the odds, why I put log n, why I didn't put log e? I just want to emphasize the word. This thing is natural log. Okay, so you can see that for the natural log, the value drops. Okay, so it becomes 0 when it is equal 50 and 50. So natural log of 1 is 0. Okay, so if you have a low high cholesterol level here, it is minus. So if you have high cholesterol level, it is positive. Okay, so this is negative, this is positive. So that's the difference between log E and so you can see here. So you have this is in terms of probability. This one is in terms of odds. This one is in terms of natural log. So this is logit. This is the concept of the log of the odds is called logit. Okay. So how it is seems to be applied in our scenario. Okay. So if we have a solution like this, male and female. Okay. So male, there are 41 with high cholesterol, 51 who are normal. Okay. So the total number is 92. So the log, the natural log of this value, 41, divide by 51, you get minus 0.21. As for the female, only 15 out of 108 has high cholesterol. So 15 out of 108 have got high cholesterol. So the log is minus 1.8. So when you divide, okay, this value against this value, Okay, so you want to find the difference of the high cholesterol level between these two groups. The logit it become 1.6. The logit become 1.6. Okay, so logistic regression. This is simple logistic regression. Okay, so you can see that the logit for sex is 1.6. Okay, you can get the odds ratio out of the 1.6, and you can say who is more higher to get the problem of high cholesterol compared to. But if you do directly, yeah, you do directly, the odds ratio also can. So let's just do the odds ratio directly. Okay, so the OR AD over BC. Okay, oops, I forgot the equal symbol. So you can see here, if you convert the natural log, the logit of 1.6, you inverse the value of the 1.6, you end up with a odds ratio of 5 times. So male are 5 times more likely to have high cholesterol compared to females. Okay, so that is the explanation about how we do logistic regression. Okay, the advantage is by using logit. Okay, so I'm going to stop sharing now. I'm going to shift the screen. Okay, so let's shift the screen back to the lecture itself. Right now I cannot find my lecture. Okay, that's the lecture. Okay, I'm very sorry. As I said it's now, the biggest problem trying to do the whole thing without a technician supporting you. You end up something like this. Okay, so I hope that's clear. I hope that's clear about the concept of logistic regression. Okay, and that is how the logistic itself is derived. So right now you're seeing the PowerPoint, my PowerPoint about odds ratio. So already explained about this. So let's go to the next one. So exponent beta is equivalent to as the odds ratio. We already mentioned this. Because if we quote as 1 and 0, if we quote as 1 and 0, so the odds of having a disease for smoker is exponent beta 0 plus beta 1. So since beta 0 is 0, so you end up at the value become beta 1. So you can see here, okay. So the probabilities look like this, okay, 1 minus p, okay. So the odds of having a disease for smoker is exponent beta 0 plus beta 1. The odds of having a disease for the non-smoker is exponent beta 0. So exponent beta 0 divided by exponent beta 0 plus beta 1 divided by exponent beta 0, it become like this. Okay. So since this one and this one is the same, this one divide by this one, you end up with exponent beta 1. So that is why we can get the odds ratio for the risk factor in causing the disease by inverting the exponent value of the maximum likelihood estimators from the logistic regression, and that's why we get the odds ratio. Doctor, can the odds ratio be converted to become relative risk? Yes, it is possible. Okay, but that one we're not covering today. Okay, instead, I will share the link the link of the article inside inside the Facebook later. All right. Okay. So when to use logistic regression? Okay, you use logistic regression when the outcome is categorical dichotomous. Yeah. If it's dichotomous, you can use the binary logistic regression. What is dichotomous? Okay, remember what I said? You marry two, you die. Dichotomous. So if you got two possible outcome, okay, dichotomous. Okay, yes or no. Hypertensive or not hypertensive. SGA babies or normal babies. Hypercholesterolemia or not having hypercholesterolemia. If the outcome is ordinal in nature, okay, like underweight, normal weight, overweight, obese, then we use ordinal logistic regression. However, if the outcome variable is more than two levels and they are nominal, nominal means there's no difference in terms of order. Example, race, you have Malay, Chinese, Indian, and others. And that one you use multinomial logistic regression. McFadden came up with this multinomial logistic regression, and he received a Nobel Prize for this concept, this multinomial logistic regression. When I can't recall, I think 1980. You can always look it up. Or was it 2007? I can't remember. I really cannot remember. Okay, so the principles are the same like in very hard to adjust. Principles are the same like multiple linear regression. Okay, so the process of modeling is the same. Yes, anything? Okay. The process is the same like in multiple linear regression. Okay. The theory of independent effect in dealing with the confounding and interactions are the same like in MLR. Okay. Ayo. I got internet problem. Okay. So they keep saying that I got internet problem. Okay, never mind. So we just do our best with what we have. Okay. So it is the same. Why? Because it is a linear model, but the outcome is from 0 and 1, from the categorical, is now changed to become log odds. And as mentioned just now, the log of the odds is continuous. It's not. It became like it has similar like linear continuous data, and you end up with a model similar like linear regression. So there are other things that uses the same approach for Poisson regression for count data, cost regression for survival data. So and these are, since they are all using linear regression model, but the data are originally not continuous. Instead, they are either categorical, like in dichotomy, like in logistic regression, or survival data for COX. Therefore, these are called generalized linear model. Linear model. It's not as GLM per se. This is different kind of G. They generalized model, linear model. So this one not really GLM, this GLM, but this GLM different. Okay. So what are the differences? So in the first differences, instead of using the least square method, okay, those who cannot recall what I mean by least square method, you have to refer back to my notes on linear regression. This one, the model is determined by maximum likelihood. So instead of calling this regression coefficient, they are not called regression coefficient. Instead, they are called MLE. MLE short for maximum likelihood estimators. So in multiple linear regression, we interpret the beta coefficients directly. So we use the beta value directly. In logistic regression, is- instead of taking the value of the MLE directly, the beta, we exponent the beta. So we exponent the beta. So when we exponent the beta, we get the odds ratio, and we discuss based on the odds ratio. And the assumptions are different between multiple linear regression and multiple logistic regression. Even the symbol should be different. So for multiple linear regression, we use the MLR. For the multiple logistic regression, we use M log R. Okay, we use M log R. Okay, so steps in handling M log R. Okay, first we do data exploration, we do descriptive statistic. For Ayub, he used simple logistic regression. I don't like simple logistic regression. I prefer chi-square. Why I prefer chi-square? I like to look at the rate. I like to look at the rate. The rate of disease among the exposed compared to the rate of disease among the non-exposed. Okay. My apologies about the loud noise. My neighbor about 4 doors away is having renovation. What to do? Uh, Lives like that. Okay. I hope you all can hear me lah. Okay, so we'll be checking for the step 3, which is variable selection, which one should be inside the mean effect model. Then we check for interaction and multicollinearity. Uh, then we look at the model assumption and outliers, interpretation and data presentation. Okay, so for this, okay, I wish I can do the SPSS and this together at the same time, but I cannot because I'll be jumping too many times from the different screen. Okay, so I'll be showing you the slides only. At the end, I will try to show the how to do the multiple logistic regression using SPSS, so that we just go one round, okay, from start till the end. So here they're showing the how to use logistic regression one by one for the simple logistic regression. So first, we the outcome of interest is hypercortisolemia. Where to get data? It is from the same website. We already put that out there on the same website, drtimer.me. Okay. So we have the hypercall for the outcome. We have all the risk factors. What are the risk factors? They are age, sex, diabetes mellitus, hypertension, and exercise. Okay. So which one to quote as the reference group? The reference group should be the group with the lower risk. The reference group should be the group with the lower risk. So you have to look at your data. You look at your data. That's why I say chi-square is better, because chi-square you can see the rate of the disease among the exposed and the rate of the disease among the non-exposed. So here in this case, the males, lelaki, has higher risk compared to females. Therefore, you have to use female as the reference group. Inside this data, female is coded as 0, male is coded as 1. Okay, so therefore, when you set the data set, you have to code a reference category as first. Reference category as first, so that female become the reference group. Okay, the other thing about logistic regression, please code everything as 0 and 1. Please code everything as 0 and 1. Why 0 and 1? Okay, right now you're all getting a headache. Why? Because my camera keeps zooming in, zooming out, zooming out. Sorry. Ah, there's a problem when you use an action camera as your streaming camera. I got two other cameras for streaming. GoPro, SJ Cam. Later I will try it out. Which one is better? Because this Insta camera keep zooming in, zooming out. It's causing me a headache also. Okay? So you have to code everything as 0 and 1. Why 0 and 1? Those coded as 0 should be those of the lower risk. 1 should be coded for the higher risk. You must remember. So this one is based on absent and present. Cannot use 1 and 2, okay? Cannot use 1 and 2. Not advisable. So you can see here, what it says that females are 5 times more likely to, sorry, males are 5 times more likely to develop hypercholesterolemia compared to females. Lelaki 5 kali ganda berpeluang mendapat hypercholesterolemia berbanding dengan perempuan. Okay. So this is how it is done. Okay, I already explained to you inside the Excel spreadsheet. So let's not go to deep with that. Okay. So you can see here we have the same results for diabetes. Okay. Diabetes got 3 categories. One is diabetes not present. One is diabetes present but controlled. Then you have diabetes poorly controlled. So you have DM0, DM1, DM2. So the reference group should be the DM0. The diabetes mellitus not present. Okay. And everything will be compared against the other group. So you can see here, those whose diabetes is uncontrolled are 5 times more likely to get hypercholesterolemia compared to those diabetes who are controlled, which is 2 times more likely. Okay. So in short, in summary, so this is the summary of the table. See, the camera keeps zooming in, zooming out. Why I did not use the SJ cam? There's no lobang. There's no lobang. There's no hole for me to poke the wire. So the waterproof casing that I got do not have a hole. Insta360 has got a hole there, so I can plug in the wire. And the camera cannot stand on its own without the without the casing. That's why I'm still using the Insta. Although I got the SJ cam and the GoPro. The GoPro got lobang, but the lobang cannot use because the opening cannot be open. The casing cannot be open. Okay, so we already saw the results here. So in summary, based on the results, for the age it is significant, for the sex, gender it is significant, for the diabetes it is significant only for the control diabetes, which is weird. It is only significant for the control. The uncontrolled one is not significant. Hypertension not significant. Exercise it is significant. I like PKP. Why I like PKP? Every day I can go and exercise with my wife. Every morning we can walk 2 kilometers, 5 kilometers. Okay. So I'm getting good exercise during the PKP. Today tak sempat. Because uh, I got to attend this lecture. Okay. We use the LR. Okay. LR is short form for likelihood ratio. Okay. I'm still okay. Okay, look at the variable selection. We put in everything there. Okay, just remember about the reference group. Is it first? Is it last? Okay. Why we use indicator? Indicator coding is for 1 and 0. You use simple, it is 0.5 and minus 0.5. You end up with the same results, but it is better to use indicator. Alright, so you run the analysis. You will get these results. Okay, this one is for the forward and backward. They give the same result. And based on the same result, for the gender, male and female, they are omitted. Gender is omitted. Gender is removed. What is significant is age, exercise, diabetes. Age, exercise, and diabetes. That's the criteria I'm trying to come up. Okay, so you can see here the results. So you have the LR test, compares the likelihood of the two models, the models with age, and the model without age. Okay, so 101 versus 35. So basically, age contributes a lot. Exercise, 95 without it is 24. DM 88, 10. So there's a big difference. So when there's a big difference, it shows that these variables contribute significantly to the final model. Okay. If they are the same, then no difference. Okay, so since that's why we include the data inside there. Okay, this one, Ayub believes in testing the data that are linear, uh, whether they are also linear when you convert them to become categorical. So Ayub demonstrate this. As for me, I tend to skip this part. To me, if it is already significant and you can see the graph, they are following the same trend, I will skip this part. Okay, but this one is good in the sense that you are showing that that there is a linear relationship between the continuous data and the categorical data, and they call it a quartile plot. They call it a quartile plot. So here's some assumption. Okay, I'm not going to cover that. I mentioned this now. If the continuous data is already significant, I accept that they are significant. But Ayub believes in testing and proving that there is a linear relationship if the data for continuous is converted to become categorical. Okay, the next one is checking for interaction. The next one is checking for interaction. Okay, based on the final model, we have three final models. We have diabetes, we have age, and we have exercise. So this we have to check whether they have interaction with one another. Okay, so when we run the analysis, we check. Okay, so remember we had only three variable, so we have only three variable. So the variable are DM, exercise, age. So what we do inside SPSS, we select age, we select DM together, then we press this button. We press this button. Then they will combine these two variables together into here. So this is the interaction item. We want to see whether there's any interaction between age and diabetes mellitus. Okay. You run the analysis, see whether it is significant or not. You can see here, everything is not significant except for diabetes mellitus and exercise. Okay, so you can see here age and DM not significant, DM exercise significant, age and exercise not significant. Remember, you do it one by one. So first you put age and DM, you run. Then you take out the age and DM, then you put age and age and exercise. Then you run. Then you put the exercise and DM. Then you run. Okay, so that's why you do it 3 times, because you got uh, three variables inside the final model, and the 3 variables you can combine. You can get up to how many interaction items. All right. So you can see here you got 3 H and DM, DM exercise, H and exercise. Okay. So we have a problem here. Why? We found that DM and exercise has a significant interaction. Okay, and you have to include that inside the final model. So your final model now includes H, DM, exercise, and DM with exercise interaction. Next is checking for multicollinearity. Okay. If the independent variables are highly correlated, then our regression model is said to be statistically not stable. Okay. So what does it mean? Maybe those who are highly interacted with one another, they end up cancelling each other. For example, in Malaysia, the biggest problem that we found is religion and race. If you find religion to be significant and you find race also to be significant, they tend to be, because they mean similar in nature. Malay tends to be Muslim, non-Malay tends to be non-Muslim. Okay, so when you have that kind of scenario, remember about the issue of multicollinearity. If you run the analysis with race and religion together, they will cancel out each other. Okay, you have to take only one. I know there's a court case ongoing, uh, but I'm not going to touch on that. Uh, about race and religion. Okay, so then you have to check for multicollinearity. Okay. Ayub says there is no way to check for multicollinearity under logistic regression. Okay, but YH Chan says you can check by looking at the standard error. YH Chan says you can check by looking at standard error. If the standard error is larger than 5, if the standard error is larger than 5, then you have issues of multicollinearity. This one, they just trying to check for multicollinearity inside linear regression. Okay, so you run the same data set, age, DM, exercise inside the multiple linear regression, but you click on collinearity diagnostic. Then you look at the tolerance and VIF. Ayub discussed based on the VIF. Ayub discussed based on the VIF. It should not be larger than 10. It should not be larger than 10. Okay. If you look at Wai Chan discussed based on tolerance. Wai Chan based on tolerance. For him, the cutoff point is 0.6 for this. Okay. So anything less than 0.6 is considered as issues of multicollinearity. Okay, so you can check out the notes on Waishan on this matter. Okay, so as I said before, for multicollinearity, if you don't want to check using multiple linear regression, can you just look at the standard error. If the standard error is less than 5, you are okay. Okay, doctor, what you
Prof.
mean by standard error? Okay, I will go back. Okay, I will show you where is the
Prof.
standard error. Yeah, yes.
Sorry, Prof. Yang variation influential factor tadi,
Ah,
uh, actually apa Prof?
tak, basically they are the same variable. They are one and same variable explaining the same thing.
So,
If
apa kita...
you have a variance, okay,
Uh-huh.
you have variance larger than 10 VIF, okay, indicates that that variable is the same. They are highly correlated with one another.
If more than 10.
If the VIF is more than 10, let's say you got the H and DM is more than 10, then H and DM is highly correlated with one another.
Okay.
But the example I gave earlier was race and religion. I find a lot of that SKSP. So I missed that. It was picked up at the Viva level, so it was quite embarrassing for me. So the other thing I mentioned about the standard error not being larger than 5, I'm talking about this standard error. Can you see this? Okay. If there are standard error of larger than 5, then you have issues of multicollinearity. Doctor, how to decide which one to take out? My style, I take out one with the largest standard error. Then I run the test. See whether the model is stable or not. Okay? Okay, I hope that's clear. Okay. But remember, multiple logistic regression does not come out in your exam. We are teaching this only for your project next year. Alright, so that's the important thing. Why? So that you all don't panic. Otherwise, I don't want you all get panic attack. Trouble lah. Okay, so let's go next part. The other part is the Hosmer-Lemeshow test. The other part is the Hosmer-Lemeshow test. I like this slide. Okay, I use slide very nice and clear, so I can be inside the slide without affecting the PowerPoint. Okay, so let's look at this value. Okay, we can run, when we run the analysis, we can click on the Hosmer-Lemeshow test. So when you click on the Hosmer-Lemeshow test, you want it not to become significant. You want it not to become significant. So here it is not significant. Okay, so what does it mean? It means that the model fits well, the dataset fits well to the logistic model, and the relationship pattern is not different from the theoretical logistical model. However, Hosmer-Lemeshow may have problems if your sample size is too large. If your sample size is too large, Hosmer-Lemeshow may become significant, although your data is beautiful. Although your data it fits the model very well. So please take note of that. So Hosmer-Lemeshow test also got some problem if the sample size is too big. Okay. Next, we look at the sensitivity and specificity. So we look at sensitivity and specificity. Basically, you're trying to see whether the predicted model based on the final theory is similar like what you are observing now. Okay. So basically, you are observing. So you can see here inside this data set, they coded as 1 and 2. They coded as 1 and 2. Okay. Here is the prediction. based on the model, okay, when you run the analysis, you can ask for the prediction. If the value is larger than 0.5, means they will develop the disease. If the value is less than 0.5, means they will not develop the disease. So here, no, not hypercholesterolemia, hypercholesterolemia, not. Okay. So this one is the outcome of interest. In this data, they coded the hypercol as 2, the not having hypercol as 1. So you can see that it does not match. Tidak tepat. It is not accurate. So we're looking at overall, this is the accuracy. Okay. So we have specificity, we have the sensitivity. Alright. So, doctor, what you mean sensitivity specific? This table inside SPSS is inverted compared to what we are used to. Okay. For what we are used to, it is the other way around. Left side, the test at the top is the gold standard. So here, this is the gold standard. This is the test. So it is inverted. So for those who are having problem, please invert the values. Please invert the tables. Okay, once you invert the tables, then you can see the sensitivity and specificity the usual way. Okay, you want to see how good is your model in predicting whether the patient develop the disease or not. Okay, dang. I hope that's clear. Inside class, usually what I do, I will redraw the table back using the whiteboard and show the angguk-angguk geleng-geleng. That tends to make it clear. Okay. So this one, 83.5% were accurately predicted. The sensitivity of the test is 64.3%. Sorry, sensitivity of the model is 64.3%. Specificity of the model is 91%. So it's quite good. Okay. Okay. Then you have to check for outliers. You have to check for Cook's inflation statistic. You just click on probabilities and Cook's under options. Okay. So you can see that these are the predicted probability. The cutoff point is 1.0. So you can see there is none larger than 1.0. Therefore, your data is okay. Sorry about that. Okay. Ding. Okay. So finally, this is the final model. This is the final model. Remember, we have come up with another table earlier. The table earlier is for simple logistic regression. This one is for the multiple logistic regression. So what's the difference? Some data has been dropped out. Some data has been dropped out. What was dropped out? Those that were not significant. So you have here, you have the adjusted OR for age, for diabetes mellitus. Okay. So a bit weird. Yeah. It's 137 for uncontrolled. It looks like inverted, this one. Yeah, just have a look balik. Diabetes mellitus. Okay, this one DM1 and DM2. So for the DM1, DM2, from what I understand, DM1 is between between control and between not diabetic and control diabetes. Control diabetes for 4.9. But this one we have to check back at the notes. So when we run the analysis, they will tell you what is DM1, what is DM2. So here it is not stated, but never mind, we will do this later ourselves. Then we will know whether the table is correct or not. Okay. So now it's very hard to say because you can see here we have the M1, the M2. Both are significant. Okay. But once we include the exercise factor, suddenly the one become highly inflated. Okay. So very sorry about that. So let's go and look at the last part. The last part is where we control for the interaction. So how to interpret? So based on this table, we have to report about the model fitness, outlier, the pseudo R squared. Okay. So pseudo R squared in the text. Because of interaction, we can only interpret H which does not involve in the interaction items. Okay. DM and exercise, we have to further run the analysis because they have some effect of interaction. So you can see here, okay, age no problem. So older you are slightly higher odds of having hypoglycemia. Okay, so 1.32 is not a lot. You have to remember 1 is the no effect. So if 1.32 is 0.32, why? Because 1.32 minus 1. So 1.32 minus 1. So 1.32 minus 1. So 32% more odds of having hypoglycemia compared to those 30 years old. So please take note, you get 1.32, 1.32, 1 no difference. So 1.32 minus 1, you get 0.32. That's why it is 32%. Okay, the effect. Okay, so we have a problem, as mentioned just now. Our problem is the interaction between diabetes mellitus and exercise. So what you do? You run it separately with different selection. So this one, the first round, you run the selection for those who don't exercise. So you see, for those who don't exercise, no effect. The odds ratio are not significant. So 1.2, 0.121, 0.558. So the diabetes mellitus are not significant. Okay. So the odds ratio of the M among those who do not exercise are not significant. Okay. I hope you can see this. The odds ratio for those who do not exercise, the difference is not significant. So, next level. Adoy. There was a problem of loading this page. Subhanallah. Okay, download. Does not matter. Okay. So right now I have to download the file. Okay, I'm going to open up the slide. Okay, I'm going to change the screen being shared. Sorry, I did not realize that thing happened. So I'm going to share the. Kejap. The first thing first, I need to move this thing to a different screen. So now it is on a different screen. I click view. I set full screen mode. So now what happen now on my screen? Susah nak ngajar. Now I have to set it to Adobe. Okay, so the Adobe is up. Okay. Now the screen I'm sharing with you all has to be changed to become the Adobe screen. I don't think I got the Adobe screen here. Let's try again. Screen 3. Okay. I hope you're seeing what I'm seeing right now, which is okay. Sorry. I'm getting slightly confused because I got so many screens here. My apologies. Okay. Okay. So what is happening now? We are showing you the screen for, we're trying to control for the interaction. So to control for the interaction, we have to code the data accordingly. So you have to change the data for those who exercise and those who do not exercise. So right now you're seeing this slide. Okay, these are odds ratio for those who exercise. Okay, and those who do not exercise. So this is those who do not exercise. So you can see those who don't exercise, no effect, not significant. Okay, the odds ratio are not significant. So the odds ratio for those DM1 and DM2 is 2.286 and 1.427. Okay, and they are not significant. Why they are not significant? Because they cross the value of 1. But when we run the data for those who do exercise, wow, suddenly become significant. Suddenly become significant. So for those who's, okay, if I'm not mistaken, the DM2 is for those who have uncontrolled diabetes. So for those who have uncontrolled diabetes, the exponent beta is 250. The exponent beta is 250. So what does it mean? A lot of these people end up becoming hypercholesterolemia. So somehow, people whose diabetes is not well controlled, if they exercise, they end up with worse hypercholesterolemia problem. Wow. I'm not going to try to explain that biologically. Okay. The biological possibility does not make sense. Okay. So apparently those who are having uncontrolled diabetes mellitus, if they exercise, they end up with worse outcome. Okay. Why does this thing happen? because the numbers are different. Because the numbers are different. Those who do not exercise, the n is 98. Those who exercise, the n is 102. These are two different group of population. Okay. For those who do exercise, the odds ratio for controlled diabetes mellitus is 4.62. For uncontrolled diabetes mellitus is 250. So it shows that the effect of DM is different between those who do exercise and those who do not exercise. And that is the interaction. Okay. So based on this one, remember they say DM2 is for uncontrolled DM. So therefore the discussion here is terbalik. The discussion here is terbalik. Okay. DM2. Okay. DM2. From just now we got the odds ratio is 250. Okay. So somehow it is missing here. The odds ratio. This one got 0.59. Something wrong here. But here, yes, odds ratio is 107. Okay, for uncontrolled. For control, it is not significant. 4 times. Alright. So that's so the DM1 is for control DM. The DM2 is for uncontrolled DM. Alright. Okay. So that is the issue. Okay. So I do not know. Okay. How come the explanation is different? Okay. But I can see here the exponent beta for those who exercise are higher. The risk of hypercholesterolemia is higher among those with diabetes which is uncontrolled. Alright, okay. And this one, then you do the same thing the other way around. So the other way around is we set for exercise and not exercise. The selection variable is 0, 1, and 2. 0, no diabetes. 1, diabetes well controlled. 2, diabetes not well controlled. You have the exponent beta of 31, 18, and 0.342. Okay, so this one not significant, this one significant. So this significant for these two. So there's a difference between those who exercise and those who don't exercise. So among those who diabetes is well controlled, exercise, that is good for you. Less risk of developing hypercholesterolemia. This one, those who are diabetic and exercise, you can see here, is 18 times more if you don't exercise. This one, 31 times more if you don't exercise. Alright. So, among the things, if the interaction is with a numerical variable, this one the interaction was with continuous data, with categorical data. So it is diabetes mellitus and exercise. So then you can check for interaction. So if the outcome is numerical, you have to come up with you have to change the numerical data to become dichotomous, and then run the same way. Okay. So when you run for the model for interpretation of interaction, the effect of the variables might change. Don't worry about that. Okay. Please take note. The minute you run for interaction, okay, we're done. Okay. So I'm going to stop. I'm going to stop sharing now. Okay. I'm going to open the floor to questions. Sorry, tak sempat buat SPSS. Already almost time's up. This topic was quite hard to cover in enough time. Why? It is quite a heavy topic. Today I just added the origin of logistic regression, so it made the whole thing become worse. All right. Any question? So, last time who was it yang rajin tanya tu? Fatihah.
Fatihah.
Fatihah. So Fatihah, happy now?
Okay lah
Happy?
Prof, tapi interaction tu macam complicated sikit.
Memang complicated. So that's why we always hope when we run the analysis, tak ada interaction.
Betul Prof.
So,
Tapi Prof, certain statistician dia kata macam kita ignore je interaction tu, sebab kalau ada interaction tu nanti lagi apa macam Prof cakap tadi, dia akan jadi sampel lagi kurang semua.
yep. Tapi itulah, bila dah ada interaction, tak nak kena explain kenapa ada interaction. Kalau kita ignore terus, without taking that into consideration, nampak benar kita menipu kan. Lepas tu satu lagi, kita kena declare when we run the interaction and kita buat apa. That's why I declared it. N92. Okay. Prof, I used to see variables in univariate analysis with p-value of 0.25 and less can be included in M-blot R model. Okay. By the way, it's not M-blot, M-log. Nabi Lut tak termasuk kat sini. Cerita Nabi Lut tak masuk sini. Okay. Why 0.25? Okay, this one I know who you read. Is Rosna Ismail. Rosna Ismail always emphasize on that 0.25. Yes. If you start with a lot of variables, you run the analysis, then you want to decide which one to include into the final analysis. Usually you use based on two decisions. One, you base on the literature that you read, which variable should be inside the final model, and the other one is based on the p-value. So which p-value to take? Okay, if you take a 0.05, then you're already taking only those that are significant. But sometimes some of the variables, like just now you saw the diabetes for well controlled, the p-value was 0.09. They are just above 0.05, but they are almost significant. So sometimes variables that are almost significant, once you adjust it for all the confounding factors, they become significant. That's why, to be sure that you have not missed any of the variable that may be significant, you use the 0.25. Okay, so why 0.25? Because of that. In case there are those variables that were almost significant but became not significant due to effect of confounding factors, by controlling for the confounding factors, you hope to have the value to be from 0.25 to become less than 0.05. Personally, in my experience, that has only happened once. Okay, so I will not be too sure of that. And the other issue is, if you want to include that variable, you must make sure there are no issues of missing value. If there are issues of missing value, you end up with a very, very, very small sample size. Okay, so that is why that issue has to be taken into account. Alright.
Prof, yang ni kita tak belajar lagi kan model fitness.
Model fitness, whether the model fit or not.
Ah,
Kat sini kita ambil shortcut. Kita ambil Hosmer-Lemeshow. Tak, that you have to understand. The department has tasked me with something impossible. Not only I'm supposed to teach you all basic statistics that I'm going to ask you all in exam, but I'm also supposed to teach you advanced statistics, which you're going to use for your project next semester. So I have to pick and choose lah what topic I can cover. And so for this one, for the model fitness, I take the shortcut. I just say, okay, you just use Hosmer-Lemeshow. Okay, so at least Hosmer-Lemeshow. Okay, when we cover GLM, repeated measures, that one we will cover a lot about model fitness, about all the different variety. Okay, so maknanya as I cover each one of the topic, I will cover about model fitness bit by bit, based on the different tests. It is not a standalone topic by itself lah. You have to understand. I myself did not have a good exposure in this. Okay, you have to understand that when we started way back in 1997, okay, so we do not have the benefit of good lectures on this topic. We had lecturers who are more interested in how the formula is derived rather than how the formula is applied and how to interpret the results. So when we started taking over in 2003, okay, when we started in 2000, it was just me and Rizal. And when we taught is on the application side of advanced statistics. And it is based on our own reading. Ni kalau ikut agama salah ni, belajar tak ada cikgu ni. Okay, I had the good fortune of attending a workshop by Prof. Ayub, and Prof. Ayub made the whole thing become clearer. And that's why for some topics we use his notes for lectures, because his notes are very, very clear. So we are doing the best that we can based on what little we have earlier to make this curriculum as comprehensive as possible and as applicable as possible. Okay, and this, if you check the file kursus, the proforma, the course proforma, from 2003 until now, every semester it changed. Every semester it changed, so that it becomes better and better for you all. Okay, so the aim here is so that whatever you do is applicable. Just imagine lah, last semester we started teaching R. Last semester we started teaching R because we believe that you all should know R. Okay, KKM only asked us to make sure you all learn Stata. We did teach Stata. Okay, now we are adding R, so you all hopefully become better. So that's why you see for this semester, because I'm teaching you all basic stats, after I've covered the basic stats systematically, now we are covering the advanced topic. And but the advanced topic we cover is based on what I think is your required knowledge for next semester's project. So the first week we covered about questionnaire validation. Then we covered about controlling for confounders. Today we covered about multiple logistic regression. And why we cover? Because Fatihah tanya lah. Alright. Okay, so and with that, I think can we end for today? Ke ada soalan lagi?
Ada salam, Prof.
Yes, Jen.
Yeah.
Jane.
Yeah. Just now there is this step 4.1 and 4.2. 4.1 is checking interaction and 4.2 multicollinearity. Multicollinearity just now, as Prof said, it's like two variable highly correlated, like
Religion and race.
yes. What about interaction? How do we explain that interaction? Because gonna do two, right?
The interaction we already showed is now the DM and exercise. For the multicollinearity is more about is under that one lah. As mentioned just now, you look at the standard error, you look at the VIF, you look at the tolerance. Uh, the interaction we already covered just now. We run the test for interaction.
And another last question.
Uh-huh.
Let's say that we have many variables in one study. Let's say more than 10, and we have to check like one by one. And end up we might have to check for like 20 or 30. Let's say we find like one or two interaction. Do we still deal with it like the step number 6 just now? Sorry, step
Yes.
number 5. Yeah.
Yeah, so that's why you always, whenever you run the analysis, you always hope and pray that there is no interaction. I tell you lah, during this for the DRPH program, I think we got 2 cases where there is issues of interaction. Okay, so it was very difficult trying to explain to the external examiner about the interaction, because not many people are aware of this issue on how you're supposed to analyze data when there is interaction. So in fact, some are just saying that, as mentioned by Fatiha, ignore je. Okay, just before you put in the final multivariate analysis, you look at the p-value, whether they are worthwhile putting in or not. Then you also look at the literature review, whether there is any biological plausibility for that variable to be inside the model. Okay, so otherwise, if there's no need for it to be inside there, don't put. Okay, then you don't have that problem.
Okay, thank you.
Okay, all right, thank you very much. Okay, I'm going to stop the lecture here. Okay, lupa, first foremost, stop recording. I keep forgetting that. Okay, stop recording. Okay, now I'm going to go to the Facebook. I'm going to stop the Facebook. Okay, bye bye Facebook. Bye. Okay.